Let's now discuss differentials. As with a function of just one variable, the approximation delta f approximately equal to the partial of f with respect to x at x naught y naught times delta x plus the partial of f with respect to y of x naught y naught times delta y has a convenient formulation in the language of differentials. If f of xy is differentiable at the point x naught y naught, we define the differential df to be the partial of f with respect to x at x naught y naught times dx plus the partial of f with respect to y at x naught y naught times dy, where df is a dependent variable and dx and dy are independent variables, and we refer to df as the total differential of f at x naught y naught. We can use df to estimate the change in the function f, where dx is the change in x and dy is the change in y. As an example, let's use the total differential to approximate the change in f of xy equals x squared plus y squared from its value at 1, 2 to its value at 1.003, 2.004. For f of xy equals x squared plus y squared, we have that f of 1, 2 is 1 squared plus 2 squared, which is equal to 1 plus 4, or 5. Also, we have that the total differential df is the partial of f with respect to x times dx plus the partial of f with respect to y times dy, which in this case is 2x times dx plus 2y times dy. Evaluating this differential at 1, 2, with dx equaling the change in x, which in this case is 1.003 minus 1, or 0.003, and where dy is the change in y, which in this case is 2.004 minus 2, which is equal to 0.004, we have the following. The differential df in this case is 2 times 1 times the delta x value of 0.003 plus 2 times the delta y value of 0.004, and this evaluates to 0.022. We can compare this to the actual change in f. We know that f at 1.003, 2.004 is equal to, when we evaluate it, 5.022025. And we can compute the change in f by looking at the difference between f evaluated at 1.003, 2.004 and f evaluated at 1, 2. Computing this change, we get 0.022025. The error in approximating delta f by df has magnitude, absolute value of 0.022 minus 0.022025. This evaluates to 0.000025. Note that the distance between the point 1, 2 and 1.003, 2.004 is, when we calculate it, 0.005. And so we have the ratio of the magnitude in the error of the approximation to the magnitude of the distance between the 2 points being 1/20. Thus, the magnitude of the error in the approximation is 1/20 the distance between the 2 points 1, 2 and 1.003, 2.004. Indeed, this is what we want. We want the magnitude of the error in the approximation to be much smaller than the magnitude of the distance between the 2 points.